Water is found in different states on Earth, which completes a cycle. Liquid as ocean and rain, gas as water vapor in the atmosphere, or solid as snow or ice that we found in polar ice sheets such as Antarctica. A water molecule consists of one oxygen and two hydrogen atoms. In nature, these elements exist in different forms called isotopes, which have the same number of protons but differ in the number of neutrons in their nuclei, resulting in varied masses. As a result, we have different forms of water molecules, commonly referred to as water isotopes. The water isotope ratio varies due to the successive fractionation process that occurs at each phase transition in the water cycle, starting from the oceanic regions where the moisture forms to the condensation sites where snowfall takes place. Lighter isotopes are preferentially found in the water vapor state during a phase transition, hence leading to a relatively high proportion of heavy isotopes in the condensed phases. Water vapor is progressively depleted in heavy isotopes by successive precipitation events along its path from evaporation above the ocean to the snow formation in polar regions. The proportion of heavy oxygen in glaciers is influenced by temperature, with colder climates showing a more pronounced discrepancy between lighter and heavier water molecules. As new layers form, older layers become buried, allowing deeper layers to provide insights into past temperatures through the isotopic content of solid water. In each step of the water cycle, we will find both heavier and lighter isotopes. The ratio, compared to the ratio of a standard, gives the isotopic composition of water expressed in delta notation. The isotopic composition archived in polar ice cores responds to temperature variability. Scientists have extracted a linear relationship between water isotopes and the mean annual temperature of the site, and they developed the isotopic paleothermometer. But understanding the natural pacing of past temperature variabilities through the water isotope signal is more complicated, especially when we are talking about deep cores where we have extremely thin old layers that are challenging to measure, or if we think about all the processes that may alter the water isotope signal before it is buried in the ice or even after that. That's why scientists' efforts are focused on developing cutting-edge analytical techniques and models that allow for high-accuracy past temperature reconstructions and predictions for future climate. I'm part of the PICE project because I enjoy working in diverse environments, both inside and outside the lab, and this comes together with my appreciation for nature.